Welcome to The Torch of Progress. This is the speaker series for Progress Studies for Young Scholars, our online high school program focused on the history of technology. Progress Studies for Young Scholars was offered initially over the summer as a summer program and is now being run each semester as an after-school program or part of the online virtual offerings of the Academy of Thought and Industry. And to find out more, you can go to progressstudies.school. In this series, we talk to a wide variety of people who know either about the history of progress or the practice of progress and the cutting edge. And today we have someone who knows a bit about both. Our guest today is Manjari Narayan. Manjari has a Ph.D. from Rice University and is currently a postdoctoral researcher at Stanford University School of Medicine. She also happens to be my wife, which is why we're live in the studio together today, being quarantine buddies, and I guess we're a pod. I am your host, Jason Crawford. I write The Roots of Progress, where I write about the history of technology and the philosophy of progress, and I'm the creator of the high school program, Progress Studies for Young Scholars. Welcome to the program, Manjari. Thanks for taking the time.
Great to be here.
So, statistics. We're going to talk about a few things today. We're going to talk a bit about the history of statistics and some about the current, its relationship to science, and maybe if we have time, a little bit about its relationship to machine learning. But I want to start with the history. When you say statistics, I think a lot of people, when they hear that word, probably is a little abstract, maybe seems a little boring, kind of mathy, not even quite as cool as calculus. Although I think it's getting cooler, these days. But statistics actually has a fascinating history, and it's really important in the story of progress because people, it turns out, wanted to use it for a lot of important things, for improving agriculture and how we grow crops, for improving medicine, how we understand disease and test out treatments, and for things like manufacturing, making better products. And I see maybe our video has gotten a bit blurry again. Sorry about that, having slight technical problems with the video. Hope that helps. So I want us to just start. Manjari, you're not an expert on the history of statistics, but you know more about it than anybody I've ever talked to. So I thought we could have a fun conversation starting off by some of those topics. Let's start with agriculture. This goes way back. What are some of the origins of statistics in agriculture?
So in the early 20th century, around 1919 or so, I guess in Great Britain, there was this research station called the Rothamsted Research Station that had been investigating crop science for a long time. And they decided to hire a preeminent statistician, Ronald Fisher, to come work for them. And so this was, I think Fisher was like, didn't have an academic appointment somewhere else, and so this was the moment the head of the research station talked to Fisher. He was like, oh my God, this guy's a genius. I just have to hire him. And so that's how Fisher started working at this agricultural research station and basically invented a lot of statistical methods precisely to understand all the factors that lead to improvement in crop yields. And so he was very influential there in terms of helping them figure out how to efficiently investigate all the different factors that affect crop yields. And one of the things he noticed was that if you want to do experiments, one factor at a time, you'll just be here forever. And so he started thinking about, well, how can we actually learn from, growing crops on different plots of land more efficiently, without having to wait forever to do every experiment. And so that was kind of the origin. And really it was a kind of virtuous cycle. Like statistics itself as a field didn't exist. But because Fisher was hired and working at this agricultural research station, he just applied his thinking to this problem. And not only did it improve our thinking about agriculture, it improved the field. I mean, it just gave birth to the field of statistics in a sense, and a lot of statistical thinking.
Yeah, the very word statistics used to mean something kind of different, didn't it, in the 19th century?
Yeah, so I'm actually not sure about the usage of the word itself before in the 19th century versus the 20th century. But so for example, most people, when they think of the word statistics, what probably comes to mind is just the notion of like summaries of data. You know, we think about vital statistics, you know, how many people, what are the birth rates and death rates in a country, you know, how many, think about the census and the data collected in a census about who lives where and how old they are and so forth. So I think the original term statistics just referred to summaries of data, like creating aggregate summaries from data in the vital statistics sense. But it was really in the early 20th century that people started to think about, like, what is it that distinguishes, you know, when do numbers turn into facts? Like the theory of thinking about, you know, this is like my kind of spiel, you know, numbers are not facts. Like we need a theory that tells us like when and under what circumstances they really can be. And so, you know, since the 20th century and since the birth of the field of statistics, statistics is more the science of telling us when numbers tell you something useful. It's, I think one person put it as being a sort of a rigorous and constructive skeptic about numbers. That is, by default, numbers don't mean anything. But if you are careful enough about how you acquire them and how you summarize them, then maybe they can be meaningful.
Yeah, it almost sounds like a riddle. When is a number not a fact? That's a fascinating perspective of going from just summaries of numbers to actually when can we trust the numbers. I mean, in a way, and I think you've said this to me before, statistics is like it's like applied epistemology, or I think quantitative epistemology.
Yes, that's right. Yeah. I think there's a number of statisticians, myself included, who you know, in quotes, call ourselves quantitative epistemologists. Yeah. You know, we're not just like, oh, we're not number crunchers. We're not like people who analyze data or something. Like we actually, like for us, it's about interrogating the procedures by which we analyze our data. Like that's what makes somebody a statistician.
Yeah. Yeah. So if epistemology is sort of the study of how do we know what we know, statistics is kind of how do we know what we know about numbers and measurement, certain, how do we get quantitative knowledge? Yeah, fascinating. Now, we were just talking about agriculture and you mentioned Fisher. Now, I know he's a big name in the history of statistics. What did he do? What's some of his biggest contributions?
So he, in a sense, he's, you know, he is the father of modern statistical thinking. You know, I probably can't even list all the different contributions he made.
Maybe one or two big ones.
But you know, the notion of experimental design or design of experiments is something that Fisher introduced. He also very deeply, the other big, to my mind, so this is certainly biased towards like my perspective, I think the biggest change is that pre-Fisher, you know, people who were statisticians never specifically separated the notion of, you know, what is the target that you seek to understand from data? You know, what is the procedure by which you are getting some estimates of this target? And how do we evaluate this procedure? So this sort of like separation of what is your target or the thing to be estimated, the estimand. Find a model that describes how, you know, your estimand and a model produces the data. Then figure out a way of creating a procedure to infer this unknown quantity. So he was the first person to kind of draw this distinction of the estimand, the estimator, which is the procedure for inferring an estimand, and an estimate, which is like the particular numerical quantity you might get after applying an estimator to data. And so he was the first person to make this very elegant distinction between all these things and to say that we should quantify the behavior of our procedures and understand the precision or uncertainty around them. And so he was the first person to really introduce this in a much more rigorous way than before. And that, I think, that's fundamentally one of the things that changed after Fisher.
Wow. Now, as I recall, some of these early agricultural experiments, isn't this also one of the first places that somebody, I don't know if it was Fisher or who, had the idea of doing randomization Randomized
Fisher.
trials. Yeah.
Yes.
So that was one of his.
So it wasn't randomized trials, but it introduced the notion of randomization. So for example, let's say you have like multiple plots of land or fields. You want to understand, factors that improve crop yields. And let's say there's like two factors you want to consider, like irrigation methods and fertilizer. And so he came up with a wide variety of techniques to answer this kind of question, all the way from how should you actually acquire this, conduct the study, to acquire this data, and then procedures for analyzing the results of the experiment. So when we talk about like design of experiments, for example, he thought about, well, how should we actually vary the factors with in this kind of setup? So you have the crops that you can plant and you have the fields that you can plant them in. And so what he proposed is that the things that are hard to vary, something like irrigation, it's hard to vary irrigation methods easily. You might only be able to vary an irrigation method from field to field. So he would take the hard to change or manipulate factor like irrigation methods and randomly allocate them to different fields. And then within a field, you can split the field in a way that makes both parts of the field, the split plot, sort of equivalent to each other. And he would randomly allocate, for example, the fertilizer to each, to one or the other side of the split plot. And then once you collect data from this, he designed methods to basically quantify, how likely is it that we would see as extreme a difference in crop yields from, say, fertilizer A versus fertilizer B, had they really been equivalent and nothing really varied, and, what is the probability of having seen an extreme difference had the two fertilizers effectively been equivalent? That was a notion of, creating a control and developing notion of precision of like, well, if we can't explain, if random chance can't explain as extreme of a difference that we see, then we can assign, attribute it to the difference in the fertilizer, for example. So he really developed a lot of techniques there to do this kind of thing, including random assignment in this fashion. But his goal when using randomization there was to really develop accurate, realistic measures of uncertainty.
Coming back to the epistemology point.
Yeah.
When we talk about randomized trials, probably a lot of people, their mind first goes to medicine. This is another key place. So talk a little bit about some of the origins of medical statistics.
So again, I'm not I'm not an expert by any means in the history of medicine, but so I believe the earliest usage of thinking about clinical trial design was in the context of understanding the efficacy of streptomycin as an antibiotic. And Bradford Hill, in that context, came up with this idea, before, I think he was the first person to really demand that we use this notion of random assignment of a treatment versus a placebo to different groups in order to study the efficacy of a treatment. And so in that context, in medicine, if you let a person self-select whether or not they will take a treatment or a placebo, there could be various things about people themselves that are different between the ones who are willing to, maybe the sicker people are willing to take the risk of taking the real drug, while the less sick folks might prefer to just take the placebo, something like that. So you can't really, figure out, what aspect of people getting better can be really attributed to the treatment if you let people choose their own treatment, for example. So he was the first person to really demand that, doctors can't really know what works without using this kind of experimental manipulation and assignment of the treatment. But I believe from reading somebody who is really a historian of like statistics in medicine, Harry Marks, that Bradford Hill's adoption of randomization in clinical trials was almost independent of the usage of randomization in biology and agricultural experiments.
Wow. It's
It
kind
was
of
only later
independently
on,
invented.
or maybe only loosely inspired, because it turns out that back in the 30s and 40s, statisticians were very involved in this field called biometry, which was like biological research. But biological research was considered very separate from like clinical work, and statisticians were practically not involved in that area yet. Like today, people associate statisticians with being involved in medicine, and that wasn't the case in that time.
Yeah. And randomized clinical trials were actually quite controversial for quite a long time, right? There was actually there's really a moral dilemma around them for some people. I know when I read about the Salk vaccine trials for the polio vaccine, Salk himself was very much against this concept that they were going to do a placebo-controlled trial, because he was so convinced that it worked, and it was this polio was this epidemic that was striking in waves every summer. And as far as Salk was concerned, if you did a placebo-controlled trial, you'd just be failing to protect half of the children who were going to be potentially paralyzed. And so he saw that as a real deep moral dilemma. Ultimately, they did do. They actually, in the case of the Salk vaccine, they did a combination of. They did some randomized controlled trials, and then they did some other trials where all the volunteers for the trial got the vaccine. So more than half it was a very large study, hundreds of thousands of children, and more than half of them ended up getting the vaccine. But a portion of it was done as a proper, because the other scientists who were evaluating insisted that we do a proper randomized control. But that was in 1955, so
Yeah.
As late as that, it was controversial technique. Now, of course, it's totally standard.
That I think it's very easy for scientists to tell themselves that things work even when they don't. And so this is part of the skepticism. You know, it was very difficult. I think I still can't believe that somehow in the span of 20 to 30 years, you know, like methodologists actually convinced doctors that they had to do RCTs to evaluate treatments, and that they couldn't just tell, you know, from looking at the data, because there's so many sources of like human bias.
Yeah.
And doing that.
Yeah, totally. All right, let's talk about the one other area, which is manufacturing. So it's a disparate area from these others, but statistics also very important in getting sort of precision, high quality products. So say a little bit about that, maybe some of the origins and history.
So I do know of like at least, you know, one extremely influential statistician, George Box, who, if you don't know his name, you've certainly heard the quote, you know, all models are wrong, some are useful, which is, he's the one responsible, the culprit for that. I prefer some of his other, one of my, you know, I have other quotes of his that are, I think I'm much more fond of. But he was very influential in this idea of bringing experimentation and statistical thinking to manufacturing. I believe he even wrote an essay at one point saying, you know, quality improvement was like the new industrial revolution or something like this.
Everybody likes to say that everything is the next industrial revolution. Yeah.
But you can imagine there's something very similar to the crop yield example I mentioned earlier to manufacturing. You know, when one thing in high throughput manufacturing is understanding, well, can we go faster? Can we go faster? Can we make things, can we make more units in a smaller amount of time without losing quality? Or can we detect anomalies? Can we find out the products that don't meet our quality requirements and like get rid of them automatically? If so, what are the references? How do we determine that automatically? Things like that. So this whole notion of design of experiments that was going on in agriculture, people quickly realized that this was extremely important in the context of manufacturing. So I believe chemical plants, as well as, you know, manufacturing, both of them quickly adopted, you know, statistical thinking to think about the quality of their products and to think about, you know, understanding all the factors that could lead to increasing, say, production without reducing quality. And it's the same kind of problem. In fact, Bach's notes sort of that people's intuitions would be to like, there's like 100 factors. Here, let's vary one thing at a time and like study what improves and what doesn't. And this is most people's intuition. It's a fairly good one. But what the statisticians had already realized was that it makes much more sense to vary all of them in specialized ways at the same time, because you can learn much more information about what works and what doesn't by studying varying linear combinations of factors in very clever ways. And so the whole design of experiments is all about this. It's about cleverly varying multiple factors at a time such that you can figure out, you know, what helps and what doesn't very quickly.
That's really surprising to me, actually, because you hear, you know, when you learn about the scientific method or how to do experiments, I thought one of the basic kind of pieces of wisdom is you only vary one thing at a time, so that when something changes, you know what was the cause. You're saying it's actually makes more sense to vary many things at once. How do you figure out any sort of causation if you're varying multiple variables?
I mean, the key thing is when everything is under your control, you can decide how to vary multiple things at once. And so in the design of experiments, people will talk about the design part of experimental design is exactly to think about what are the patterns in which you vary things. So you can imagine there's a notion of creating patterns that are effectively independent of each other. And so the idea is to mimic the situation of where you vary one thing at a time, but instead you're varying patterns of things at a time that are all behaving as though they're independent of each other. That's the bottom line. And so if every factor is under your control, you can do this. But if nature is the one giving you information, you can't do this. You know, and that's the kind of difference between sciences where everything is under your control versus areas where only a few things or almost nothing is under your control.
And ultimately, it's, if I understand this, you're saying that we do this for efficiency. There are many variables we want to control. If we only varied one at a time, there'd be way too many experiments to do. So we vary multiple at a time in clever ways, and then use statistics to tease apart the differences and the correlations.
Exactly.
Yeah, that makes sense. And it reminds me of, I guess, coming a little more to the present, some of the present challenges in statistics, and forgive me if I use some terminology wrong here, but have to do with what is known as high dimensional statistics, where now maybe we're trying to understand the effect not even of hundreds of variables, but maybe tens of thousands of variables on, you know, on some outcome.
Yeah, so I think in the last 25 years, there's sort of two regimes that we operate in that differs from, you know, classical statistics era that we were talking about. And they're both considered high dimensional regimes. So broadly speaking, what that means is there's two scenarios. One, which is you're very likely to encounter in medicine, where, for example, consider cancer biology. We're trying to understand what are the factors in cellular and molecular processes that influence, you know, the fact that we get cancer, and we want to study what can eliminate cancer or cure cancer. So there's like lots of factors in your body, in your environment, all of which we're able to measure. And we want to use all of that to determine, well, who is at risk, who is likely to get cancer, you know, what treatments work, and so forth. And so the difficulty here is the number of people you're able to collect measurements on is going to be on the scale of tens, hundreds, or thousands. But the number of variables involved can be in the thousands, tens of thousands. You know, at this point, we can even be on the scale of millions. And so the number of unknowns in our model is like much, much larger than the number of data points we have available. And what this effectively means is that there's going to be multiple configurations or multiple families of models that are likely to explain the data equally well. And so we have to figure out ways of like taking into account, you know, things that we already know about the data, about biology, such that, you know, with minimal assumptions, for example, assuming that, you know, the cause of cancer are ultimately more simple. Like there's not actually a million things that affect cancer. There's maybe thousands of things amongst the millions of things. And so just making that assumption, for example, that it's actually only a thousands of factors rather than a million, that's like an example of an assumption you can enforce to draw conclusions better. And so high dimensional statistics is this field that tries to figure out, how can we draw inferences from data in this kind of scenario? The other kind of scenario is where the data you collect and the complexity both continue to increase without bounds. So you can imagine things like people's purchasing behavior for lots of products that's constantly changing over time. The more data you collect, it's not the same pattern over and over again. It's like the pattern is itself changing. So the more data you collect, the more complexity there is in the data to understand. And so this is a scenario where both the data is increasing and somehow the underlying complexity of the phenomenon is also increasing at the same time. And this is a different kind of regime that's also where, statistics is a very active, but the solutions all differ.
Is there a term for that?
It's the other, in statistics, you might say high dimensional, low sample size and high dimensional, high sample size.
Okay.
They're both high dimensional.
So these would both be under high dimensional statistics.
Yeah.
Got it. Interesting. Okay, great. Let's go some to, I know people would be curious to hear about the replication crisis. It's said that we have a replication crisis in science. How do you think about this?
So lots of varying thoughts. One, I think it's been a long time coming in the sense that, many areas of science, and science here, we can think about it in a very inclusive way. Science includes not just the life sciences, but any kind of quantitative science like engineering disciplines, machine learning, where people do synthetic or data analytic experiments and so forth. So if you think about all of research, all of science broadly, we've effectively, we're doing very complicated things. We rely on computers and very complicated processes to collect data and draw inferences on data. And we've never really adapted and asked ourselves if the way we conduct science and do science is well suited to working. So oftentimes, and part of this is related to publishing culture, like once you investigate something, you do it one time, and you publish a paper and you forget about it. And so it turns out there's lots of results, both in the life sciences and even in what you could call computational sciences, where it turns out that our results really don't hold. The next time a researcher tries to do something, they find out that they're not able to reproduce the exact result. And so I think a lot of people began to realize that there is some kind of a methodological reform necessary in the culture of doing science, because clearly a paper is not evidence that we've actually accomplished something. A paper, I think a well-known statistician, he says, a paper is just the marketing that you did something. Like the fact that something actually works and that knowledge has been produced, like that's not a guarantee. And so we're, slowly trying to figure out this gap between, the culture of publishing our results in papers versus, the actual results, and when these results hold and not. And that's broadly, I would say, there's an overall concern about methodology and reforming methodology in science, not just in the life sciences, but particularly in the life sciences. I think what people have come to realize is that there's a lot of what you could call background factors that go into collection of your data and go into analysis of your data that we never really write down or put anywhere, but they kind of influence whether or not the second time a person tries to repeat a result, whether or not they will find the same finding again. And so I would say people are beginning to, this is sort of a symptom that there is a problem in science, the fact that either we are not doing the right experiments, or we don't know enough about what we're studying, that we think we are capturing and telling everybody exactly what we did, but we're missing things that we didn't even know. Yeah. And that's, this is happening. There's a fair bit of self-awareness of this issue in the context of psychology, but really from my point of view, every field of science is, almost every field of science, especially a lot of the life sciences, have this, this concern is everywhere. Something that people may be less aware of is that people also attempted, replicating what, like maybe 50 of what were considered seminal papers in cancer biology and cancer studies. And, I think they were able to get much less than half. And so this is a concern across many areas of science. There's a replication crisis in machine learning where people realize there's lots of papers that say we developed this new technique and this beat the benchmark and our method performed really well, and then somebody else tries to do it and they find out it doesn't work. And so there's a growing concern that we need to do a better job of this. But it is a fairly complex issue because one of the problems with the term itself is that it means different things to different people. For a statistician like myself, a very basic check is that forget collecting a new data or new experiment. Can I just reuse the same data and code and data and environment and just produce an answer? There's like the notion of computational reproducibility. And so the lines are a little bit blurry, but you can separate sort of issues of, this kind of same input, same output in a very controlled way, which you could call computational reproducibility, versus do we understand the phenomenon well enough that we're able to take somebody's description of an experiment, repeat it, and get the same phenomenon again. And the fact is, just because something doesn't replicate, it doesn't necessarily automatically imply that the first study was wrong or that the second study was wrong. It's a very subtle issue. There's natural variation between study to study just because you're recruiting different participants. Like there's small, minor variations between one study and another. And it could be well due to chance that things don't match up. So it's a very subtle issue deciding what on earth it means that two studies, when you collect a new data set, don't replicate.
You mentioned to me once that you thought maybe even the term replication crisis was not the ideal way to think about it. What's wrong with that term, or what's a better way to think about the issue?
I think one thing to keep in mind is that the fact that something you thought ought to replicate or was a stable phenomenon doesn't replicate is an important symptom. It's an important sort of indicator that we keep track of. But just because things don't replicate, it doesn't mean that I think we should optimize science towards replication. Like everything shouldn't be judged from the perspective of, oh, it's true if it replicates. We shouldn't confuse truth for replication, because it's quite possible that any scientific phenomena, you can think about there being as like a sort of tree of hypotheses that span the space of like what we want to explore or what we want to learn. And if we incorrectly focus on maybe a part of that tree that's like less likely to be true, and worry a lot about whether or not put all our resources into trying to replicate something, or only a small portion of that space, then you might be missing the opportunity to just ask a better question somewhere else and test a different hypothesis. So it's not even clear that all the things we worry about not replicating is even worth trying to replicate. We all have like, fixed time, energy, resources, and motivation. And so an equally important aspect of scientific, methodological reform in science is to not just ask questions that are easy to ask or have been asked before, but to ask new and different questions that might be more informative. And that's often the hard part of science. It's sort of, it's very easy to try to get a more precise answer to an old question that's already been asked, rather than asking a new question where, you might get less precise answers. You have less mature techniques and tools, but it might be a more fruitful direction.
Yeah. A lot of solutions have been proposed to the replication crisis, or at least things that might be able to make it better. What of those are you, if any, are you most optimistic about?
One thing that one word you'll hear a lot about is, getting rid of significance testing or p-values. Mm-hmm. The other thing you'll hear a lot about is pre-registration. I think both of those things need rethinking. And it's, one thing is, one mistake that people made that even statisticians never anticipated, I think, was trying to think that we can evaluate the results of a paper with like one summary statistic. So, for members of the audience who might not be familiar, a lot of the results of a study might be often summarized with p-values, which are a statistic that are meant to indicate a degree of surprise. Like if the phenomenon you were studying, if the null hypothesis were true, then a p-value indicates, well, this is a very surprising result to get if the null hypothesis were true. That's effectively what it gives you. But ultimately, a p-value tells you, did your method have the capacity for answering this question with good error control? It doesn't really tell you if a hypothesis was true or not. It doesn't tell a person, did you ask a good question or not? It doesn't tell you, was your experimental design good or not? Or did you have good controls or bad controls? It's very easy to get a small p-value, which indicates, hey, we have found some discrepancy against the null and found some evidence, in favor of our hypothesis. But if you just use bad controls, you can get small p-values, which look desirable, but don't actually evaluate the quality of your study. And so the overemphasis on p-values, I think, and moving away from that and encouraging maybe a more holistic notion of evaluating a paper is, I think, really important. And I think, statisticians themselves internally never thought that p-values were the end all and be all, but that somehow became encoded into the culture of science. And so kind of undoing that is, I think, important.
Yeah.
Which I'm a fan of p-values because they're good for a very precise thing they were designed to do. They weren't meant to become like a gatekeeper for whether or not a study should be published.
Interesting. Okay, great. We will take questions from the audience in just a few minutes. So if you have questions, go ahead and put them in the Zoom chat here. For anybody who is in our, if you're in one of our programs, go ahead and ask questions in the private. I want to talk a bit about machine learning. What is the relationship between statistics and machine learning? What's the difference? Are they the same thing?
This is one of these very, controversial questions. So there's sort of two sides of machine learning. And one is sort of like the theory and mathematical part. And one is more about the sort of applied machine learning in industry. Really, the word means many things to many people. So it really depends on what we're talking about. So I would say one big difference is that the culture of where machine learning problems came about, it's a subfield of computer science, came about because we want to, computer scientists wanted to automate drawing inferences from data, so to speak. So things like, providing recommendations, automatically labeling your photos, these sorts of operations we have, people realized that you can do a much better job of, completing a question that you want to type into a search engine, or labeling images or classifying images automatically. If you take statistical principles and figure out how to make them work at scale. And in this context, and so in a certain sense, I think, one way that I think about it is statistics is the application or extension of statistical thinking for certain domain areas like computer vision and natural language processing and, recommendation systems and so forth. And so in one sense, I find that it's really not any different, except that the culture and the questions being asked, like statistics tends to focus more on maybe science and medicine today, and machine learning focuses more on these, modern industrial questions. It's like one is just a difference of application. But there are some slightly more foundational differences too. In, I think, statistics, we maybe, certain applications, we have much more information to take into account. And so we're willing to make stronger assumptions. Whereas in machine learning culture, you just want something that works regardless of your data. So they have a more emphasis on what people call non-parametrics or weaker assumptions. But I would argue that's not really a fundamental, it's not a foundational difference. It's just more of a in practice difference. There's more varieties of, thinking about, let's model our phenomenon with as complex models as possible, as flexible and complex models as possible. And it's possible to do because the amount of data you're working with in machine learning is like on the level of millions and billions. That's not a thing you can do in like medicine. You can't collect data on millions and billions of cancer patients. We're sort of, this comes back to the two regimes of high dimensional statistics that I mentioned. Machine learning tends to focus on more, because of the kinds of applications it works with, there's both more complexity and more data coming in. Whereas in traditional biomedicine, there's always like more complexity, but less data coming in. And so they're fundamentally different regimes, but where, the statistician in me would say, well, all of machine learning, is really statistical thinking applied to very specific kinds of applications. But, we could argue a lot about that. There's a lot that's different in the operational, how data analysis is done. There's more of an engineering focus in terms of like building systems and infrastructure and pipelines and so forth. So there's a lot of like other differences like that. So if you look at specific things people are doing, there are a lot of differences. But at sort of the foundational level, statisticians want to draw principled inferences from data. Machine learning people want to automate principled inferences from data. So there's a lot more that's foundationally in common than is different.
Yeah, great. Okay, we have a slight technical issue here, which is a low laptop battery. So I'm going to run and fix that. And while I do that, I'm going to give you the first question from the audience. So Juan David, who is one of our students in Progress Studies for Young Scholars, asks, what is the best way to learn statistics and why do you think we should learn it? So let me go run and grab the power.
So let me answer the why question first, why you should learn statistics. I think one reason that everybody should learn something about statistical thinking is that, every area of work today, whether it's in science or industry, it's all based on making decisions based on algorithms operating on data. And the best training you can get for thinking and evaluating, the procedures or algorithms by which, that are influencing our lives is training in statistics. So I think that's one reason why everybody needs some statistical literacy, because it teaches you how to figure out and evaluate procedures like algorithms operating on data. As about how to go about learning statistics, I would encourage, for most people, I think it helps to start with a, current day question or application that seems to produce a lot of data and that you want to use to make certain decisions or learn something about the world. And, but to remain a kind of skeptic about, whether those conclusions are correct or not. And sort of pick up courses and maybe data analysis competitions that help you do this kind of activity with like sort of some amount of guidance. So I would say, practically speaking, take a few Coursera courses, sign up for a few Kaggle competitions, learn to analyze data, but then then as you go along, figure out, well, how would you go about interrogating your procedures for analyzing data? And there's amazing courses on Coursera right now taught by some of the best statisticians in the world. Harvard Biostatistics, Johns Hopkins Biostatistics, courses from Stanford edX. They all offer some really, I think, very accessible and high quality courses in statistics. And I would combine that with some kind of data analysis, question of interest to you, and sort of play around with that and learn from there.
Great. It occurs to me that statistics is not a thing that maybe a lot of people think they're going to go into even at the high school level. Maybe they get into it in undergrad, especially for some of the younger folks in our audience who might still be in school. And might be really interesting if you'd be willing to share kind of what was some of your own path. What did you think you were going to do in high school? How did that change, and through college? How did you ultimately get into statistics?
So at the high school level, I think a lot of statistics that I encountered was of the vital statistics variety. It was all about creating, means and percentiles and medians and data. And I thought it was like the most boring thing. It was the most boring, useless crap. Like I clearly had no idea what statistics was. But my path to realizing I enjoyed statistics, I went into electrical engineering, and in there I was drawn to the mathematical side of electrical engineering, signal processing, which is all about the analysis of signals. And it turns out that statistics and signal processing have a long shared history as a consequence of Bell Labs. And as a consequence, so much of what I enjoyed about signal processing was like the statistical aspect. So, in the world wars, people were designing radars to detect, is there a plane in the sky or not? And they had to decide based on noisy measurements, do we decide, there's a plane or not a plane? What is the error control there? What's the cost of a misdetection versus a false alarm? And so radar signal processing was all about, making these decisions continuously over time, for example, to detect whether or not there's a plane, an enemy aircraft or something. Similarly, transmitting signals, and your cell phone communication is filled with statistical thinking, wireless communications, because you basically have a signal that you design that you want to transmit across a noisy channel, and it needs to be decoded at the end. And so statistical thinking really had to go into, how can we take noisy, corrupted measurements at the end and figure out what was sent earlier? And that was really a statistical problem. And so I discovered these sorts of
Isn't Claude
things.
Shannon's information theory, which he developed while at Bell Labs, isn't that in essence a statistical theory of information?
It was slightly separate from statistics, but information theory and statistics are very much siblings in a sense. What he did was, he certainly used probability theory in his theory of communication, and certainly statistics plays a huge component. But Shannon introduced fundamentally new mathematical concepts of this notion of like the capacity of a channel to transmit information. Like he came up with fundamentally distinct concepts that didn't exist in statistics, but people realized they were really useful to each other.
This reminds me of another common maybe confusion or lack of clarity about statistics. What's the difference between probability and statistics?
So that's a great question. So probability so probability is an area of mathematics, while statistics is really an area of science. That's the first distinction. So probability just says, I can take some phenomenon like the flipping of a coin and create a model for saying, if the probability of, if a coin is like unbiased, then here's the probability of getting heads and here's the probability of getting tails. So this is purely a generative description of, given an unbiased coin, here's a way of describing sequences of coin flips. And that's a probability model. Statistics is about drawing inferences about unknowns. So statistics is more about given data, what can I say about the unknowns that generated the data? So it's about going the other way. And so that's fundamentally, even though statistics uses mathematics, it's not a branch of math. A lot of statisticians will tell you that statistics is not a branch of mathematics. In fact, John Tukey, who started out as did a bachelor's in chemistry, did a PhD in applied topology, like pure mathematics, famously said, statistics is not a branch of mathematics. And he was a mathematician enough, to own, it being a branch of mathematics, if that's what it was. But he fundamentally did not think that was the case at all. It was all about drawing inferences from data. And I think that's what makes statistics different.
Okay, so back to your story. You got interested in signal processing, and you mentioned that has a lot of statistics.
So I really enjoyed that in my undergraduate work. In fact, I loved my probability and statistics class so much, but I did everything from scratch, did not prepare for my tests, practically had a really bad grade. And I was so mad, I took the class again and effortlessly got an honors level score in it. But that's just to say, I actually got bad grades in probability and statistics, and I'm the biggest stats nerd, I could find today. So I really enjoyed it, and I decided to pursue that area in graduate school. But I quickly became more interested in applications of science than engineering, and that's how I switched more to formal statistics and biostatistics compared to electrical engineering. So, I don't have any degrees in statistics, but I in practice I do.
Yeah, you basically switched about halfway through grad school or so. So yeah, it took you a long time to come around. It's funny that you thought statistics was boring in high school, because I thought that history was boring in high school and all through college, actually. Well, and statistics too, but history in particular. Now here I am spending full time on the history of technology. So we both came around to our different topics. Okay, great. Any audience, if there's any other questions, go ahead and just put them in the Zoom chat. There's a question that I like to ask everybody who comes on this series, especially for the high schoolers in the audience. What is sort of a piece of common advice or common wisdom for teenagers that you think is actually wrong, and what would you replace it with?
So, let's see. I think one, it's sort of, I think some people, I think there's common wisdom. I don't know if it's current wisdom to high schoolers, but people always tell you to find something passionate to work on. And I think it's true. It's very important to find that, but sometimes you don't yet have it. And I think in the meantime, shouldn't shy away from doing things that make you uncomfortable or that you're not good at. So I would sort of, pursue things that you might not be good at for a while, because what I've discovered is that things that I'm not good at, I eventually get much better at with time. You can make leaps of changes, and then suddenly that that opens the door to finding something that you might be truly passionate about. And so but you wouldn't have gotten there if you hadn't like persisted in the interim. So I think it's about striking a sort of, you should really try to strike a nuanced balance between being uncomfortable and finding things that are easy to work on, but don't lose sight of finding something that you're passionate about, but don't expect to know it when you're in high school. It might take you a while to get there, and I think it's worth waiting. Also, don't go to grad school until you have a problem you're passionate about solving. That's another thing. You're not there yet, but you know, it's probably something you'll start to think about when you're in undergrad. And
yeah, no, that sounds like very good advice. Yeah, it seems like maybe if you don't have that problem you want to solve, maybe instead of going to grad school right away, you should go into industry for a while. Or
yeah, as statisticians say, we like to play in everybody's backyard. So I think that's actually, I think that's a great lesson for everybody. I think you should just try lots of different things, like learn about the problems in the world today before you go think about it more deeply or get a PhD in trying to solve something.
Okay, great. Well, I think that's a great note to end on. Manjari, if people want to know more about your work or follow you, should it be Twitter? What's the best way for them to?
Twitter is pretty good, yeah.
And your Twitter handle is?
Neurostats.
Neurostats on Twitter. I am also on Twitter as Jason Crawford, and you can find my work at The Roots of Progress, rootsofprogress.org. And if you want to learn more about our high school program, Progress Studies for Young Scholars, go to progressstudies.school. Thanks again. This is a great conversation.
Glad to be here. Yeah.
All right. Thanks, everybody. Until next time.